All right, so anyways, this is my 1 hour survey of the entire field of mobile robotics, essentially. This is going to be a very high level overview of essentially, I want to get robot from A to B. I'll get more into details and like what the scope of this is in a second. But I hope this is a decent way for you to get a good idea of essentially, again, if you want to move something from A to B while fulfilling some criteria, what do you have to do, like practically, to get to that point? And should hopefully demystify autonomy in general. That's really my goal. So as I go through this, if you have questions, please ask them. Just put your hand up a little and I'll point to you, because this is going to be kind of an info dump, and I'll probably move somewhat quick through some sections. And so if things aren't clicking together yet, feel free to raise your hand and kind of ask clarifying questions, because I think that'll help everyone out quite a bit. Because I really, again, the goal of this is less to know, I know how to implement like SLAM or something, and more, I know what SLAM is and how it would apply to other things, for example. So anyways, just ask questions. It'll be good for everyone. And, oh, I'm on the wrong window. There we go. So here's our beautiful itinerary. Essentially, I'm going to be going from a really basic approach to autonomy, saying why that doesn't work, and then basically getting through the components required to logically create a sequence to solve the issue. I'll get more into that in a second. But basically, it'll slowly get kind of more advanced as we go down the pipeline. But it's kind of like a sequence, more or less. So first off, as I kind of mentioned, we kind of need the goal of why mobile robotics, and the answer is, of course, you want to get from point A to point B. This seems simple, but really, this is actually fundamentally, this is the problem you're trying to solve. Is I am here, I want to get there, and I want to have some criteria. So for example, this could be an autonomous car. This is obvious. I want to go to like Detroit and I want to not crash. But if you have like an autonomous lawnmower, this is essentially like, I don't want to just go from A to B. I want to go, follow a snake path through a yard while avoiding hitting things, for example. These are the kind of problems that mobile robotics is designed to solve. And so this is like, fundamentally, this is the problem that everything here is trying to, go towards. So first off, I want to build an extremely naive approach to this that I see a lot of like FIRST robotics teams use. And this is like kind of a, the starting place for everything else. That comes from odometry. Odometry is actually, in my opinion, a fairly complex topic. You see it thrown around a lot in robotics literature, but no one really explains it. You can see the Wikipedia definition, a classic up there. I would say, essentially, odometry it's two things. I'll get to its second use in a second. But I'd say odometry as like a piece of data essentially means a piece of data that tells you about how you moved. So for example, this could be, I went, at this moment in time, I was going 5 meters per second with an angular velocity of, half a radian per second. And that was, we were angled like facing 20 degrees down. Like that would be a piece of odometry. So I refer to odometry as like you have odom. When I'm saying that, think of motion data, essentially. And so really the reason this is so fundamental is that no matter what you're doing, odometry is how you sense your motion. It's just all of those motion sensors combined into one structure. And then obviously you'll use that to further your navigation. So I guess in this case, probably the most useful instance of odometry is dead reckoning. So dead reckoning is probably the most simple version of finding where you are that you can do. Essentially, what you do is, given all of your odometry over time, you just sum them up. So for example, if you have a bunch of velocities over time and then angles, you would just simply do the basic physics to find, I was going 5 meters per second and now it's this times sense. How far have we gone? This is where we are. So like, for example, I have on the slide, like if you're in the corner of a room, you turn 45 degrees and take 20 steps, where am I? In this case, obviously you would, be like, okay, well, we can do the geometry of we turn 45 degrees. 20 steps is like, each step is like 1.5 feet we can estimate. And then we know like kind of sort of where we are. You can start to see what may be an issue with dead reckoning, and why you can't always use it. And that's the fact that you drift like crazy. And this is like the drift in odometry. This slide right here is kind of the reason the field has to be as complex as it is. Essentially, in odometry, because all of your sensors and, for example, as we saw, like the replaying of those sensors, require estimates. But every sensor is ultimately an estimate. So like we have wheel encoders, for example. Wheel encoders literally just count your wheels turning or count your motor turning. So of course they're accurate, right? But then, let's say a wheel slips. So like a wheel is spinning really fast in mud. You were spinning your wheels, but to estimate how much you've spun your wheels equals how far you've gone would no longer be accurate, because sometimes your wheels were spinning faster and you weren't moving at all. So like that's an example. But this applies to GPS. This applies to accelerometers. This applies to everything. Like it's just fundamental to odometry. Like fundamentally, you cannot remove drift from odometry. Like that's just a reality of it. And so because of this, when you dead reckon, if you just say, play back your odometry to find where you are, there will always be error in that. And so what it actually looks like, you can see in the bottom left, is because it accumulates, this is why it's called drifting, you'll have a steady movement in some direction. I mean, it can jitter, but generally it's a steady error that accumulates and biases you away from where you want to be. And so really where this is relevant is when you want to find out where you are long term. So in the short term, this doesn't really matter because you've moved centimeters to the right in error, like who cares? But let's say if you're even, again, to autonomous lawnmower, I'm probably going to reference a bunch. If you're mowing a full yard, the error in doing, let's say, 3 vertical, out and back switchbacks, if you have 10 feet of error to the north, you're now going to plow through your fence because where you think you are is not where you actually are, right? And so really there's, again, a lot of what we're going to be going over is essentially how do we solve this issue? How do we deal with this? So before that, we have to briefly mention, of course, where that error is actually coming from. So I've mentioned these a bit. These are essentially your core sensors for odometry, in my opinion, or at least the ones we use in the club. These are encoders, which are, I think most of us know what encoders are, but they're essentially just sensors that can read how much a wheel or a motor has turned. This gives you linear position, and of course there's derivatives like velocity and etc. just by counting. This will drift over time due to slip. So if you're sitting still, this will not drift at all, which is a very important property. As you move, though, this becomes less accurate over time. The opposite is IMUs, which are a combination of accelerometer, magnometer, and gyroscope, right? It's not a gyrometer. Basically, these are just these 3 sensors in one. This estimates angular pose, which is basically pitch, roll, yaw, as well as linear acceleration and angular acceleration and velocity. So this is all of your accelerations basically, and this is mostly used for finding your rotational values, because encoders are really, really, really bad at rotational values. But IMUs are incredible for that. But they're the opposite. They're really bad for linear motion outside of acceleration. So there's a few issues with IMUs. One, you have to calibrate them. Just get a sensor that automatically calibrates. That's my answer to that one. But then 2, it accumulates error over time rather than over distance. So it's the exact opposite of encoders. So if you have a robot with an IMU, and we actually have this problem on Phoenix right now, that sits still, you'll see your odom will still drift. So even though you're sitting still, if you just dead reckon, you'll dead reckon as if you've moved. So it's the exact opposite of encoders. And then VIO, I'll reference a bunch because it's very useful. It's basically it's visual inertial odometry is what it is. Basically, given your camera and tracking what's called keyframes, or like let's say angles are generally one. Like I have a right angle here that's distinct. You track all of those right angles through an image, and then frame to frame, you look at the vectors of how those keyframes moved, and you can derive your velocity from that image. So this is extremely useful because it has very low drift comparatively. But the issue is that if you have error from things like you have a smudge on the camera, or it's too dark, or it's too bright. So you have all those issues from cameras, and it's also just expensive. But you see these on things like drones, where like you can't have an encoder, right? So this gives another source, or like submarines, this is used in, or like our go-kart even, just as another source of data if you can afford it. Afford what? Yeah, probably.
We definitely can't afford to not compute without adding.
Yeah, cameras are really expensive. I'm constantly shocked by how expensive. Well, both in price and in compute, especially. Like images are big. So, anyways, given we have drift, how do we make it more accurate? So this is without any extra technique, just making the estimations from sensors more accurate. Well, there's an entire field about this. It's called state estimation. I'm not going to go super deep into this, but just a general overview. State estimation is a field of statistics that deals with estimating the state of some variables given some measurements and some uncertainties of those measurements. So basically, the idea here is that using the state estimation, we can combine the uncertainties we have from each sensor type, which as we saw are unique between the sensor types, and do what's called sensor fusion, where essentially we take an estimate given by each of those sensors and combine them together to get basically a measurement that cancels out the uncertainties between them. So for example, a classic combination is like encoder and IMU, because encoders drift over distance, but not if you're still. IMUs are the exact opposite. So if you have both, they start to naturally, combine and cancel each other out, so to say. Now, by far the most common example of this is Kalman filters. I am not explaining Kalman filters in depth because that is like another whole lecture. But essentially, it's given Gaussian values. That's the most important part. They have to be normally distributed error. So you have a mean and standard deviation. That's what that means. And some state values, which are things that you want to estimate, and measurement values, which is what you read from your sensors. You can essentially iterate between reading real measurements, using some sort of internal estimation model, so some model of your system, to estimate what your next state would be, and then you correct that error when you read the next value. So for example, a classic one would be like you have a state variable of XYZ position and velocity, and then your measurement is position. And so in this process, you are estimating velocity. You're also estimating position, but if you don't have velocity, you can derive velocity. So if you think about this for odometry, we have XYZ position of where we are in the world that we need to find. We have all velocities, we have all angular velocities, we have all accelerations. We don't have a sensor for all of these. So what we do is we have like an 18th dimensional Kalman filter, I'm pretty sure. And essentially what you do is you take all the sensors you have, you take the bits of information you can out of them, like velocity or angular velocity or whatever, and then the Kalman filter during its estimation process with some model will go and produce what an estimation of either the variables you don't have or a smoothed, more accurate representation of the variables you do have. And so this is like how you do like intelligent debt reckoning, or just in general, you should do this to smooth your data.
Did you say 18 dimensions?
Yeah, it's ridiculous. It's huge. I used to have it on the slide. I actually took it off. Oh, he's actually using it in the bottom right corner. So this little video I just wanted to show, because this is like an example of how huge a difference this makes. So this is a little raw spot scooting around a room. Basically, the black area is real. The red area is measured. So basically, drift here is seen by those two misaligning. So you can see it's approaching a carpet. And look at it go over the carpet. Look how much it drifts, because this is just the drift from the encoders. They're not being fused with IMU. So now look, it's completely skewed. And that's because it's just that drift from the encoders slipping. So then what he does in this video is, I've lost my mouse. There's my mouse. He goes and uses, oh wow, I didn't realize he does the little thing. There we go. He goes and integrates an IMU and fuses it in the Kalman filter. And you can see he's just showing it's more accurate around the room. And then he approaches the dreaded carpet, and you can see it drifts, but way less than before. And so by purely using this Kalman filter to filter it, you haven't removed drift. Note that there is still drift. This doesn't completely solve it, but just by estimating, you've already removed a huge amount of the issue. So really, these are just showing how powerful sensor fusion can be and why it's something you'll pretty much always see in robotics, because it's so effective. Oh my god, I just want to close the video. So effective at taking the sensors you have and really using them to their utmost. Why am I not full screen? This is terrifying. There we go. So if you're using ROS for this, I just want to call this out. There is a package called robot_localization. It is not actually performing robot localization, which is very funny. But it does implement this 18-dimensional Kalman filter. This is what I use in Phoenix. I actually have it currently implemented. If you're on Phoenix, you can check that out. If you're using ROS, I'd highly, highly, highly recommend to use this. If you're not using it, try to find a Kalman filter library. They're absurdly hard to write. The actual math behind it, actually, I'd recommend looking into it. It's just statistics, but it is pretty complicated. All right, so given what we have, I guess why can't we just use odometry is kind of what I'm trying to get to here. And well, there's two main reasons. One, it drifts, as we covered pretty thoroughly now. You can't remove drift. You can help it, but you can't fundamentally you can't remove it. There will always be drift. You just have to deal with that, especially if you're over a long period of time. Secondly, it never actually as we saw, there's no actual information on obstacles. This is a way to roughly find where you are with error. However, there's no way to perceive anything about you at all. That's just not a part of this. So of course, just because we know roughly where we are, it doesn't mean we can avoid driving off a cliff. That's fundamentally we need more than just odometry. So how do we go? Where do we go from here? The next step is, I think, building a map. So essentially, seeing what's around you. And so the next kind of few sections we'll go into, we want to make a map about us to see obstacles and then ultimately avoid them is what we're building to. So first, mapping. Just straight up the map itself. So a map is the representation of the environment the robot's operating in. Generally, you'll see this as I'll get to later, essentially grids of the world. Like, for example, you can see here, this is a map of buildings in 3D. This here on the left is a cool, almost like windy maze problem of you have a autonomous ship, you have to find the most efficient path into the harbor. You can see in this case, the map is a grid, but it's not literally just raw sensor inputs. You can see it's more semantic. There's the grid squares are this is not just an obstacle, this is X or Y. So maps can be more abstract, but fundamentally it is a measurement of the environment. That's what a map is. So the most common, in my experience, and I think just in general, is what's called an occupancy grid. So an occupancy grid is what you've seen this whole time in that last video with the black squares. Essentially what this is it's just literally just an array. In this array, each cell has a probability of being filled by something. And so essentially what you do is you fill these in as you perceive your environment, and I'll get into how you generate these in a second. You will assign probabilistically, the chance of an obstacle being in a place given a bunch of sensor readings. And so what this does is it gives you this literal 2D top-down representation of your environment. It's a slice of your environment, mind you, because it's 2D, but it gives you a way to view. And of course, if you've messed with shortest path algorithms or you've seen stuff like that, you'll notice that we now have a maze. This is essentially we've created a maze, which is important because we have something we can now work with to solve. So this is ultimately that perception. Then to build up on this may just be a ROS thing, but I think this is a good paradigm. You can essentially build maps off that main map. So that's that occupancy grid is the base, and then you can build off it. So ROS's big one is called a cost map, which is essentially given every point in our occupancy grid, you inflate the area around it with cost. And so what this essentially does is, we'll see later in planning, you can plan towards essentially the safest route, where the safest route has the lowest cost, and thus if you have higher cost in your obstacles, it'll bias away from things. We learned this the hard way when we didn't have this, and the robot kept running into tables because it'll try and the shortest path is cutting the corner with literally no tolerance. And so by doing this, you essentially add a safety factor. But the cool thing is, because it's generally a gradient. So you can see in ROS, pink is really high cost, blue is lower cost. By having this gradient, you can have it so the robot can go through areas that may be more unsafe, but it'll bias away from it. Again, this is just I think it's mostly a ROS thing, but if you're using ROS, you'll see this. You can just use an occupancy grid, though. So, okay, here's where we get interesting. So, I guess, are we clear on maps and what we said so far?
Think so?
Yes? Maybe?
How do you
Yes?
generate the cost? Who generates it?
You. So you'll just have a program that takes in a map and then just looks at all those occupied squares, or extra sensor data like ROS does. It's you could have live sensor data that isn't mapped yet that you want to apply up front, and then you just generate another. This is just an array of grid squares, right? So you just take that first array of grid squares, and if you want to bubble around it, you just need some algorithm that for each, what is essentially a pixel, essentially expand that 1 pixel to 4, for example, is a way to do it, a simple way to do it. So this is all done by you. This isn't done by sensors. It's entirely just your program does it for you. Yeah. Okay. Good. Okay. Localization. So this is where things start to get off the rails a little. I'll be honest. This is where like the actual skill comes in. Up to this point, most of this I think is pretty self-explanatory. Like, oh, we have a map, duh, or like, duh, you can just count encoder text or whatever. But this is where statistics like matter. So basically, the concept of localization, as you'll hear thrown around a lot, is essentially just we have a map. Where are we? So finding where you are local to the map, or localization. So this topic is actually pretty complicated because essentially what the ultimate problem here is you have a map, you have sensor readings. Given those sensor readings, where am I? Which is a pretty broad topic, obviously. There's a lot of ways to approach this. So really there's two main, there's quite a few categories here. One, do we care about global? Like, do we care about localizing ourselves with like to the entire Earth, which some like, if you're making a drone that flies to like, bomb the Middle East or something, like you care about this. If, I could have picked a better example, I'll be honest. But if you just care about, mowing your lawn, like it's like 10 feet, like who cares? Like I don't care if my yard is relative to Canada, like it's my yard. What do you say? It's a topic. It's a topical problem. And then also we want to, in some cases we'll have a map pre-done, and in some cases we're exploring a new environment. And these two problems require different approaches, because if, for example, we're in like a warehouse and we know everything in the warehouse, we can just map this once and we just chill, But if we're like exploring the woods or something, we don't have a map of literally every inch of the US, you'll need to again look forward, be able to build a map as you explore it. And so you'll have two different approaches there. I do bring up the military just because in my experience, a lot of the people who do research into building a map as you explore is the military. Realistically, that's like the only people who do it.
I work for Tardex.
Nice. A lot of ISC alums are solving this problem.
I actually saw Joe at the Army one time.
Oh, nice. That's funny. So first, localization without mapping. This is the one that's a heck of a lot easier. You could actually implement this if you want. You do if you take our AI class. You actually implement this. It's very cool. So there's three kind of main approaches to, I have a static map. I want to find out where I am in the map. The first one is with Monte Carlo particle filters. Very fancy. It's really not, actually. You can do this. This is what you do in class. I'm not going to try to explain it because it's been long enough, but like this is like an 100 line Python program to do this. Like it's just, once you understand the statistics, the math is very simple. But generally, you can see it is actually playing out in the bottom right. Essentially, it just simulates where you could be and the probability of where you are combined with your sensor readings, how likely is that to occur, and starts filtering those down over time. That's essentially how it works. The second is Bayes filter / Markov localization. This is another one you do in class. I'm not going to explain it because I'm not explaining Markov processes, but it's just another statistical approach. 3, my favorite. This is the choice of industry, mind you. Literally, big GPS goes burr.
I was like, if we get a GPS with like close to 10 feet precision, I'll be okay with it. Just boom, boom, boom.
Okay, 10 feet is pretty bad, but.
I know, but I'll still be okay with it.
So there's two things here. First, localization for generally you want a really high precision GPS. This is like what the automotive industry does. But you can do cool things in that you have GPS, right? You also have your ODOM source. You can then make another Kalman filter, because all we do is Kalman filters, that filters the probability, the error in your GPS and your GPS with where your dead reckoning, and then filters those two together. And so that's generally what I go for small projects that doesn't have a LiDAR, basically. Because GPS is relatively affordable, it's pretty usable, with the caveat that it only works outdoors. If you're indoors, the solution doesn't work. So yeah, Mr. Lawnmower over here is pretty safe.
Do we have a LiDAR on Phoenix?
We will on Phoenix. We aren't actually doing this though. Oh no, we're just dead reckoning with really good ODOM, or really good filtering, and then we're not doing global planning. because all we need to do is be accurate in the short term and not in the long term. So we don't care about building a map because we don't have a use for it. Just locally. Just locally, to the point where drift and error we don't care about.
In your experience, how big is the map going to be in pure data sets like bytes?
That's a very good point, actually. So map resolution is actually a pretty big topic. Because you have so you have your array of squares, right?
Mm-hmm.
Generally, you have an array of the same size, and then you change, relative, but basically, how I've approached this in the past is I want like a 10 meter by 10 meter square in front of me, and then the size of that array in like literal just ints, or because remember each square is an int basically probability. However, how big that array is purely dependent on what resolution of control do I want. So a lot of this comes down to how accurate do you want your planning, and essentially this means obstacle avoidance when you hear planning in this context. We'll get to that more later. But like, let's say we're in the IVS going around tables, which was my example. If you're super hyper fine to the millimeter, doesn't really give us an advantage. So we can lower that memory use by just making them really big. But you get to a certain point where it's too big, and it's not that you'll hit something. The issue is that you'll go so far around things that it gets to the point where it can no longer find a path for you to follow, because by increasing or by lowering the resolution of the map, you effectively you making it closer to a cost map where like you're bloating everything about you. But this is pretty memory intensive, especially if you're on a microcontroller, which is what I was doing. You're going to be pushing it with the rest of the program.
I have 8 meg to work with in my microcontroller.
Yeah, I forgot what I was working with like 2, I think. I was running into issues though. I could only make a 412 by 412 array for mine, which was like,
What's your grid size?
it was 10 meters by 10 meters, which is like, I think that's an accuracy of like 6 inches.
Yeah, 30 feet divided by,
But yeah, so you can be smart about this. You don't have to just have a byte for each place. This is where the computer science comes in. If you think about it, let's say you don't care about the probability of something being there. It's either there or it isn't. Now, you're going to have false detections or false positives in this way. But if you do that, now each of those is a bit. Like your piece of information is on or off, which is a bit. That's what a bit is. It's a piece of information. So instead of having a byte for each square, you can just have a big bit array, or essentially you would have an array of chars in like C, and then in each of those chars, those are 8 grid squares.
Oh, yeah, that's smart.
And then you just do bit operations. So like you just have to find the math to find which square you want given this data structure. But like I want the very top left square would be the first byte, and then you just mask out the first bit, and then you'd find if that's positive or not. And that that divides your memory use by 8. So that's a good way to if that heuristic works for you, that's a really easy optimization and will help with memory a lot. But yeah, long story short, the answer is it uses a lot of memory, especially in huge systems. There are ways to work around it, but it all depends on your needs. Ultimately, it comes down to each application. How accurate do you need it? All right. So why can we not just do that? Because that was easy. We can just slap a GPS on it, and the GPS goes burr.
What the heck?
Okay.
Quartz and potassium.
We're big fans of quartz and potassium here at ISC. The issue is, of course, not in every scenario we don't have everything mapped out. What I just talked about only works, and this includes the GPS, mind you. You can only use just GPS if you already have an exact map about you, and whatever you're using to localize in that map, which I've kind of brushed over localization quite a bit, but like you do need a sensor for it. So generally these are LiDARs, could be cameras, but that's a big area I don't want to get into in this presentation. But fundamentally, you need to have that map in the first place. So if you don't have every single operating environment of your robot, that won't work. You'll need more. You can use GPS for localization still, but like you need other stuff. And so again, this comes up a lot in military cases a lot of time when you're exploring unknown environments. But even things like cars to an extent, frankly, your lawnmower, because you're going to different yards unless you have every yard mapped out. Or like a Roomba. Roomba's a perfect example. Roombas do this. You can see it in the app. When it shows it building that map, that's it. That's it setting up its static map. But it still has to build it because it doesn't know every house, of course. So to do this is when things get very difficult. And this is simultaneous localization and mapping, the SLAM. SLAM is absurdly complicated, so I'll just do a very, very high level of it. But essentially, SLAM is the chicken and egg problem of we want to simultaneously build a map that we don't know and also know exactly where we are. So it's essentially, I don't know, I guess maybe this doesn't seem as much of a paradox as it is when you look into it closer, but like you don't know what's around you, but you need to know where you are. But to know what's around you, you need to know where you are. And so essentially what SLAM algorithms are doing are trying to get as close as possible to simultaneous localization and mapping, because actual true simultaneous localization and mapping just mathematically isn't possible. But we try to get very close to it by rapidly localizing and creating a map about us and essentially swapping those over and over again. So you can see down at the bottom, this is what something like a map from SLAM will look like. This is us driving our robot from the lab space all the way to the back of the ELB. So like this is us leaving the building. This is the outside of the ELB. This is like the hallway in the ELB. And you can see it's very like lots of random blotches, etc. Because when you're doing this, you're not going to get perfect readings. It's going to be blotchy and it's going to be corrected over time. And that's one of the key features of modern SLAM is, they're constantly trying to make it so the map you're creating has less error and it's corrected over time, because SLAM, especially in like the 90s, would just be very blobby and almost unusable. And so that's like one of the major areas the field focuses on and one of its real challenges. Generally, LiDAR is going to be your choice for SLAM. I'll get into camera-based later. I'm actually kind of more of a fan of camera-based lately, but there's distinct advantages. First off, SLAM for LiDAR is what I'll focus on for now. There's two categories. I'm not going to get super deep into this at all. Essentially, in the olden days, they used, guess what, more common filters, our greatest friend, to estimate where they were. I've been told this is very smeary. I haven't worked with these much, but if you look into like really old ROS 1, this is what Gmapping and Hector SLAM were, just if you ever see those online. Modern SLAM, though, is all graph SLAM. I think this is very cool. It's using basically a graph of observations to estimations of where you are, and it links them with edges. It's all just a graph problem then, computer science fun. And these are what like modern SLAM algorithms like. Google Cartographer is one you'll see a bunch. SLAM Toolbox is the one we use here. Carto is like kind of just the framework that started all this off. You'll see these references if you try and learn graph SLAM. Graph SLAM isn't actually as it's hard in practicality, but if you watch there's a good like MATLAB video on it. It's actually pretty interesting to look into. Fundamentally, it's just a graph problem. It's like a algorithm like CIS 350, for example. But yeah, the actual implementation details in real life is extraordinarily complicated. I would not try and do these myself, but thankfully there are existing implementations. Here's the one I like, though, because it's much easier to understand. That is VSLAM, which is SLAM not with LiDARs, but with cameras. So if we use SLAM on like Phoenix, for example, this is what we'll use, even though we have a LiDAR. So essentially what this is taking that idea of VIO from earlier, how like we're tracking those, we have keyframes and images and we're tracking them over time. It's essentially taking that idea to the most extreme and be like, okay, I've seen an image that has these features. We then walk around a bunch. I come back to that same place, and now we go, oh, hey, I've seen that before. I know where I am. And now you have localization. The weird thing about VSLAM is that you don't actually generate a map in a 2D sense. You generate a map in like angles of images. So it's a little challenging because it doesn't give you a top-down view of your environment. Exactly.
You can derive the rest from that.
So,
Like that picture right there?
yeah, so what it's doing on the bottom right, this is actually running on, I believe, an iPhone. Oh, you can download this for iPhone. It's RTAB map. It's very fun. If you have an iPhone 11 or newer, like the high-end models, they have LiDARs in the phone. I don't think you do. I don't see the bump. Check the camera bump. Does it have a little thing on the bottom right? AR.
What?
AR.
AR?
So like AR VR can use localization to localize you within your room. So like let's say you place or Pokemon Go is a classic example.
14. That makes sense. So yeah, like augmented reality.
Exactly. Yeah.
Okay, that's
It's
fair.
Pro only, I think. But yeah,
I feel like it's almost like a reason to just drive the price up for an iPhone.
it is. I'll admit it is pretty niche, but still like.
It's still cool.
It's cool because if you think about it, AR is solving the same problem we're doing here. Where like if you don't want your Pikachu to drift across the screen, you have to localize. You're localizing it, and I think that's cool. You can see in the image, see how it's like kind of building those like gray circles around.
Yeah.
It's this here. These are the readings you get. Those blotches are the keyframes. So you can see those green circles. Those are the actual pieces of the image that just the algorithm has found as, oh, this is a unique feature that we can basically ID this physical location by. So then you can see that like kind of that like camera view. That's its estimate of your localization. And so the cool thing about VSLAM, I think by far the coolest part, is that it's three-dimensional. Because if you have a 2D slice of the world, you have no idea if you're up or down. So, but in this case, you can tell I am looking up 85 degrees, and I am, like if you squat down, it'll know that you're lower. So if you want to operate in the three-dimensional space, like with a drone, for example, is a great example, you have to use VSLAM, like straight up. That's just how it has to be done. Now,
Are we using this on Phoenix at all?
if we can't get our localization strategy to work, yeah.
Okay.
This is a fallback strategy. So VSLAM, in my opinion, has, I guess, summary just of everything I've said here. I think it has the advantages of being way cheaper because cameras are way cheaper. It's a camera. Like you can get a webcam and run this. LiDARs are like 10 grand. It's absurd. Cheap LiDAR is like 100, but you know, it's still, cameras are way more ubiquitous. You can run this on your iPhone. Like it's way easier hardware-wise. Second, it can create 3D maps. That's really hard with LiDAR. You can do it, but it's not as common in my experience. The issue with VSLAM is twofold. One, it inherits all the problems of cameras, so it doesn't work as well at night because like you can't see. And two, it if it's smudgy, if there's light in the camera, if you scratch the camera, things like that matter. And so you have to work around that. You have to calibrate the camera. It's just kind of a pain to work with the camera.
Or weather,
Weather especially, yeah. Like if it's raining, a LiDAR doesn't care. It will just it's a laser. Like who cares? But a camera will be blocked. Like they're limited by human vision essentially. And I don't think I have it on this slide. I think I found out after I made this presentation, you can actually still build a 2D map with this, and it's really cool how you do it. So certain VSLAM implementations, like RTAB map, which I've used here, this is the one I personally use, you can tag on a LiDAR scan. So it's a LiDAR scan being, you know, points about you generated from a LiDAR. Essentially what it does is for every observation, it's like a tuple of what the camera saw and what the LiDAR saw. And then essentially as just the way GraphSlam works, as you go over time and as you see like, oh, I've been here before, it can see, oh, I've been here before, and then it can basically take your ODOM and be like, I don't have error, I know where I am, and just drag your ODOM back to where you are and essentially remove all error up to this point. And that's how you remove, I should have mentioned this for SLAM in general. That's essentially what localization is you have that dead reckoned state that's like, oh, we have an error of like 300 meters, we could be anywhere in a 300 meter circle, right? But if you've seen like a keyframe, like in this case, it's easier with cameras to describe because like I see the same tree again. Like, oh, I've seen this before. I know I'm here. You no longer have that error of 300 meters. You know where you are. So you essentially like hard code your dead reckoning to be where you are, remove all error, and then you've essentially restarted your drift. So if you do this fast enough, this is called loop closing. Well, it's localization combined with loop closing. Loop closing is I've seen this place before. I know I'm here. And this is how you remove drift essentially. Is you just rapidly say, oh, I know this is where I am, and just, you know, remove that drift over and over again. And then in between you finding your next localization, you can still bear with that drift in ODOM in the short term, and then rapidly collect it so it doesn't get too big. So there'll still be drift in like feet or like a meter at worst, but you're doing it fast enough that it's only a meter. And so, you know, you can still localize while your camera's processing, but you reset it so it doesn't drift in the long term. And that's like the real fundamental point of doing SLAM. And so that's why if you do anything long term, like I mentioned with the yard before, you will essentially need something like this, I think, unless you're using GPS, which just overrides all of this. Because the GPS, yeah, so long as you can fight GPS error, because even GPS also gets hit by weather. Like if it's raining, GPS is like almost unusable. Yeah, you're in a unique scenario where I think it might actually work, but
that's kind of how I went into thinking this. It doesn't need to be perfect, right?
yeah, but you will need to do extra stuff outside of, I mean, 10 feet of error is still a ton of error for a yard. But yeah, Kalman filters will be your friend. Anyways, VSLAM can be used to build 2D maps is essentially what I was getting to there. If you do mess with this, there's two main implementations, OrbSlam, which you've probably heard of before if you've looked into autonomy, and RTAB map. RTAB map is awesome. If you have ROS, just try fooling with it. You just run the file, and it just kind of works. It's an incredible framework. You can run it off like Xbox Kinect sensors. It's hilarious. I have this on Phoenix doing VIO. It has a VIO component, and it was like literally I just ran the thing and it just worked. It's really fun to play with. It's ported to Android and iOS because why not? It's a fun group of researchers. Anyways, I'm getting way off topic. Back to what we're doing this all for, of course. So basically, what we have up to this point, we have a map of the world around us. We have our position in that map through localization, and we have ODOM, which includes estimate of our state. Obviously, this is used in localization, but we also know our velocities and stuff. Essentially, we now have, we know where we are and we're in a map, which means we can actually figure out how to get to the point we're trying to get to. Like, we're almost there now. So basically, those are the ingredients I mentioned. You have to remember to have all of these. You have to know where you are, you have to know what's around you, and you have to know your kinematic constraints of the physical robot. Given these three things, you can now do path planning. If you don't have all these three things, like for example, if you don't know where you are in the map, you don't know where A is to get to B. If you don't know what your map is, what are you going to plan on? And if you, what was my third? Oh yeah, if you don't know your physical constraints of the robot, you'll create paths you physically cannot take. So those are your three main constraints. Thankfully, this is back when things are starting to get a little easier. This is like, we've done the complex stuff. All of that work with localization and SLAM and all that nonsense was to give us this map, and now this is much easier. This is maze solving. So essentially, I guess in summary, planning is just, I have A, I have B, how do I get from A to B in the most efficient way while making a physically possible path? That is essentially all this is. So you can see on the bottom left, this is A-star. You've probably heard of A-star, actually, if you've looked into computer science. Oh, you haven't? No? Okay, so it's used all the time in game design, and of course everyone likes game design, so everyone knows it. Essentially, have you heard of Dijkstra's algorithm? No, okay. You learned this in CIS 350. Basically, it's an algorithm that finds the single most efficient path from A to B. That's all it is. But the cool thing is that it is optimal. It is literally, you cannot get a shorter path. It is the shortest path. And so what it does is, you can see it in action here. It basically iterates, biasing towards finding the next point that's closest to the goal. Essentially, it's said to be greedy in that way. It biases towards heading towards the goal. So you can see, look how it beelines at the end. Yeah. Dijkstra's algorithm, which this is based off of, will literally find every possible path and then just find the shortest one. This will only find the shortest one by biasing towards what is shortest. And so you can see, look how it makes a wrong turn here. Mm-hmm. This is because the heuristic makes it really close to the point there. That's why it's greedy. That's what it means to be a greedy algorithm. But in the average, it's more efficient. The complexity of this algorithm is ridiculous. It has like this, it has like sine or something in it. It's really funny. But yeah, so I'll get to that in 1 second. The issue with this, why would we have a different algorithm? Mainly, it doesn't include kinematic constraints. So let's say I guess I should define kinematic constraints. If you have a car and you're like, I want to go and park in the spot next to me. You cannot move the car like this. I'm backing out of my driveway. I want to go in the street. You cannot back up, spin in place, and go. Some robots you could, if they have like the cool Swiss wheels that they can spin in place, like mechanium wheels or whatever. Or whatever it's called. You can do that. Like, some things have the kinematics to do that. But a lot of vehicles, like cars or probably a lawnmower, frankly, cannot do that. So what you'll have to do is, in this plan, if your plan calls for spinning in place and you cannot follow the plan. So in like A-star, there isn't really a way to include kinematic constraints. I think you can hack it in via like hybrid approaches, but A-star, as its plain algorithm, doesn't have this. So either you need to change it or you need to use a different algorithm if you have a constrained robot like a car that can't just move in any direction. And so that's, on the right is what RTT, I think it is. What's RT? It is rapidly random trees. Essentially what it is it basically just keeps generating random splines from a starting location. I believe using some heuristic as well to get closer to the goal. And basically, as it generates these random splines, if a spline violates your kinematic constraints, it just chops it off. And so essentially, it's also somewhat greedy in that respect of it generates stuff it then has to remove. But you can see that's how it kind of grows outward as it essentially in the average finds the most efficient path. It's really interesting. I probably explained it quite poorly. Look this up if you're interested. But yeah, it's wild.
Well, wait for the point. Because the kinematic constraints, right? So it can't go.
There's some. I think it's the randomness. Because the idea is that it's random. I know the randomness is a big thing. I think it's essentially sampling. I think is the idea of like you get random points that may not be optimal, but maybe it was. You know, like let's say in like the A-star example, let's say it randomly guessed to go through the top. In the average, that may be optimal. I think that's what it's doing, but I'm not 100% sure, to be honest. But I think that's the idea. Again, look this up if you're interested. We actually had eJoy, if you know, was implementing this. I believe she did actually implement this. So like this is actually something you could implement. It's not that crazy. But you have to look at the details, I forget. I guess this is pretty much everything I've just explained. Really, there are a ton of approaches to this. There are general approaches like A-star, like RRT, or there's like hyper-domain specific approaches like we're doing for Phoenix. Or like in the bottom right, you can see like this is what inspired me to do Phoenix. This is one of the teams in the student autonomous challenge or something. It's like formula combustion but autonomous in Europe. This is like a MATLAB article explaining like how they do it. And it's essentially you take cones and then you do some cool triangulation math to find the center point, and then you drive through the center of the cones. That is a planing algorithm, but it's definitely not as generic as A-star or RRT. It's very domain specific. So I guess what the point I'm trying to say here is that you don't have to necessarily use A-star or RRT, or like actually for the lawnmower example I keep coming back to, the planer in this case I think would be like, it wouldn't be optimal for getting to A to B. It's optimal for for mowing my lawn.
Yeah, it's optimal for.
So you have to think about things like, in this case, your planner would have to include things like not missing pieces of grass between the lanes. So like doing that like serpentine path.
I don't care if it mows it.
But yeah, I mean, still, you'll have to give directions to it.
Andy, is this what planning is doing for Phoenix? Is
Yes.
pretty much that?
It's a much simpler version of that. It's my inspiration. Yeah.
We're going through the track once and then.
No, that's the difference. Is we're not. That's why I can't just use that example. If we do this, we essentially do a much simpler version of this live.
Okay.
Like on
So
reaction.
when we're actually doing it, do we just go around it once, or how does?
You could run it once, you can run it a million times. We don't keep track of global state. See, to use the method they're using, they're essentially building a map. You can think of the cones as your map in this case.
Okay.
And then notice, because you have to know about the cones across the whole thing, you have to have SLAM in this case, because you have to correct the error in drift, or else you're going to make a plan that isn't accurate to the real world because there was error in your map from drift. So that's why we can't do it in Phoenix, because we're not using SLAM for just complexity reasons.
Okay.
But that's a good point in that. And there are a million ways you could go about planning. Really, planning drives a lot of your robot. If you need a plan like this, now you need SLAM. If you can get away with not having a map at all for your planning, then you don't need a map at all. The map is for this purpose and nothing else. So if you like in Phoenix, we just react to cones in front of us. And so we have like a very short-term plan. We don't need a global map, and thus we don't need localization, thus we don't need SLAM, and we've just removed a ton of complexity.
That was kind of my plan, was to just do geofencing and say like, look, I don't really care how you get from this point to this point. It's just got to be orthogonal to some geofence, and you can't go past it. And then in between, just
Oh, like the Roomba bounce method.
yeah, essentially, but with some optimization to be, straight.
I would. Okay.
That's why I was still gonna build an obstacle map, and that was Sam and I's plan.
Interesting. I mean, if you're gonna build a map, you have to use SLAM. So you might as well do something because you have the map anyways.
The current MVP we delivered is just you map the lawn manually, so it's not.
Oh, like a Roomba. Okay.
Yeah, our literal plan is drive it around the perimeter, take GPS markers, and then that's the only setup, right? That was our long-term plan.
That's not the worst.
It's
Okay.
not great. It's
You've made essentially a static map, is what you've done.
Yeah, exactly.
Okay.
And it's not like we're trying to build the world's greatest lawnmower. We're trying to get through some
Yeah.
design.
Just think about the fact you will need to plan a path. Like the robot, even if you bounce around randomly, like, I mean, you could bounce around randomly. It's just.
I'm not gonna do random, but I'm trying to fit.
Yeah.
So I've done something like this, but for what has nothing to do with autonomy. I've done something similar for additive manufacturing, where you're given
Mhm.
a complex geometry and you plan a path that is orthogonal throughout it,
Okay.
Which respects, in our case, the kinematics are not like moving a vehicle. Kinematics are how can the tool head move? Because
Yeah, I see what you're talking about.
so,
Yeah.
So I'm gonna do something similar to that, and try to fit a grid system into there, and then use what you talked about, which is all incredibly good points to try and like optimize it.
Okay. Yeah. So essentially, you're actually doing the next step of this. So you're basically skipping planning, and going to tracking, which is interesting. Okay. Yeah. No, I think that's fair for your domain. Yeah. Anyways, very varied. Obviously, it's all domain specific.
Just need the priming quiz.
So this is something that's worth mentioning because people gloss over this a lot. They're like, "Oh, we're going from A to B with a path," and it's like, "Cool. How do I put that in a struct? Like, what am I gonna do? Have like an 80 million term polynomial? Like, let's say I have a squiggly line from here to the lab space. Like, how do I represent that? It's actually pretty simple, at least in ROS, anyways. I'm assuming this is how everyone does it. You just sample it. So like in our case for like Phoenix, we have the midpoints of all of our cones. Our path is just a bunch of those points. We call it a path, but fundamentally it's sampled points on a path. So like if you have, let's say you do actually have a fancy polynomial somehow, you would then sample, say, every inch on that, get that point where that inch would be, and then store that in a struct. And that's essentially how you represent it in memory and in your program.
It opens the door to like if you want to do digital filtering on your path.
What do you mean? No, go ahead.
I don't know what case you would use it for. If you're representing your path by a digital signal, in that case, like a list of points as a signal, can you filter it for any useful reason?
Oh, you could smooth it. Path smoothing.
Exactly.
That's actually a legitimate topic.
Average, yeah, okay, so like a second.
Yeah, no, actually that is legitimate because sometimes a sampled path can be very zigzaggy, and if you don't want to zigzag, actually ROS actually has a thing for this. For like,
Digital filter applied to that.
yeah, for like think of like a Roomba that can take smooth curves, but doesn't like zigzags. You're essentially taking a zigzaggy line and averaging and smoothing it. Yeah, no, that's a legitimate
So
use case.
Yeah, that's cool. We represent it as a signal with your digital filter. I like that idea.
Yeah, it's cool to apply theory to stuff like this.
Yeah.
All right, so thinking about this though, we now have what are I like to call them like basically breadcrumbs because we sampled our path. They're you can call them waypoints, call them breadcrumbs. But you think like again, every inch I have a point I need to get to, and if I have to follow all of them if I want to get to the end point. That's what we have now. You can't just tell the robot to go yet. Like you still have to, like you have breadcrumbs, but how do I follow them is essentially the problem. That's path tracking. So I think path tracking with knowing how paths are represented makes a lot of sense. But in my opinion, if you didn't know the breadcrumb thing, this makes no sense. Essentially, this is the lowest level of planning we have on our computer. After this, we get into hardware. Basically, this is given all those breadcrumbs, or generally it's given the breadcrumb that's next in front of me. What commands do I generate for my robotic platform that will get me to that point? So this is essentially super micro planning is essentially a way you can think about it. So generally what this means is you're generating arcs because a lot of vehicle kinematics are arcs. Like, if you're a car, you have a certain steering angle. Given the steering angle, what arc will the car follow? If you're a Roomba, same thing for diff drive. You have just if I spin my two wheels at these speeds, so that's the command you're generating, I will follow this arc. I'll stick to cars for this because I think it makes the most sense. In that case, really the only command in this for path tracking is just your steering angle, but you could also have speed. So you have like steering angle and speed. In that case, your path tracker needs to generate steering angle and speed because ultimately you're finding that arc. So this depends on your vehicle platform, what you can use to implement this. Just depends on the geometry of your vehicle and what actuators you have to move it. But ultimately, again, all you're finding is an arc, and then given that arc, your geometry of your robot, do some trigonometry, find out what commands you have to send. That's the whole idea here. There's actually quite a lot of variation, and this is a ton of implementations, interestingly. So I think the most useful for most people, because it's very easy, is Pure Pursuit. It's called Pure Pursuit because it beelines to the point and does not care what's in front of it. So this does literally zero obstacle avoidance at all. All it does is it basically finds where you are, finds the next point with some look ahead distance so you don't look 2 miles away or whatever. Finds the next point, then just does trigonometry using where you are. Again, you need to be localized for this because you need to know where you are, you need to know where that point is. Given trigonometry, you can derive the commands to get to that point just by taking an arc. That's all you have to do. There are other approaches. There is like NPC controllers, if you ever heard of them, is getting to control theory. Do like a statistical approach to like sample. We make like a bunch of paths we could take, which is the best statistically for us. If you've ever seen like autonomous drifting cars, like I have at the end of this presentation actually, that's what they use to do that. Basically, instead of modeling dynamics, you infer it statistically. Or maybe you do model the dynamics. I forget. It's a really fancy control theory I don't understand. But you can get really complex in this layer, or really simple. Or like you can include obstacle avoidance even if you want to. So like you can bias, like this is kind of what I want to do for like our go-kart. You can have like pure pursuit and then, we can also generate one without an obstacle and weight them and see like which is more, which one is less risky basically. All right, so more on what I just mentioned. This is just images of, when I say solve the geometry, this is a car. Essentially, you have this sigma, lowercase sigma, I think, is your steering angle. And then what you have here is the radius of your curve, which is about the center of your circle. So you have a circle that, your arc is following. So your arc is a segment of a circle. And then basically knowing the arc like radius essentially, or you can take the arc radius, or you can start with your wheels and work backwards. Either way, that's forward or reverse kinematics. You can just solve this because it's a circle. It's just trigonometry. So you just solve the trigonometry to find either the given an arc, what commands do I send to do that arc, or given some commands, what arc will I follow? You can do either. And likewise, over there is diff drive. That's actually very common for robots. That's how like a Roomba works. Basically, how that works is you have two wheels. Your commands are how fast do I turn my right wheel, how fast do I turn my left wheel, and there's a third caster wheel, which is just a dead wheel that just keeps the robot up, basically. Don't be stupid like we were and put 2. It only works with 1. If you put 2, it breaks. Yeah, we learned that the geometry no longer works. So we were planning as if we had 1 and we had 2, and the robot completely failed. That was Ohm for Laura's reference. It was bad. Don't do it. Yeah, it was atrocious. I guess it is worth mentioning. Obviously, all these planners working with these geometries only work if you actually implement the geometry. If you mess it up at all of these will just not work fundamentally. So just be aware. Make sure your mechanical is working as you would expect. Otherwise, you're modeling your system in a different way than it's actually working. All right. Finally, we reached hardware where this is no longer my problem. But in reality, this is where control theory kind of begins. Essentially, in this case, we have 2 commands. In control theory, these are 2 inputs. And in a car, this is I want to go X miles per hour with X steering angle. There's then the problem of, okay, cool, I want to go X miles per hour. How do I do that? And that's, this is where you get essentially cruise control of, okay, well, to get to this speed, I know which speed I'm going. I apply this much throttle, or I apply this much brake to hold this value, or same with steering. All of this comes down to control theory. I'm not getting into control theory. It's complicated, and I don't know it. But if you've done stuff with like simple PID loops, think of it like that. But this is generally implemented in hardware from what I've seen, like especially in automotive. You generate your command from the autonomous stack, and that's kind of the end of the autonomous stack. From here on out, it generally goes to like an ECU that's like on an RTOS or something for, just to make sure that loop is running at the correct speed. And then, you just assume it executes your stuff. And again, that's kind of the domain of control engineers. So you can see on the right, this is kind of a grand summary of everything. So you start with data. Or you start with sensors, gives data to perception. We haven't really talked about perception here. That's very domain specific, but that's just like I'm detecting, let's say you're making a robot that picks up trash. This would be I detect trash. This just gives you where you want to go next. Given where you want to go next, you do planning. From the V2V is just because it's from a research paper about cars. Don't ignore that. Go through that localization. Go through creating that map. Given the map, you plan. Given the plan, you track that path. Given that, that arc you want to follow, you have your commands to send to control. Send those commands to control. It executes your command, and now you have new data to process. So you start the loop over again, and this happens at like 60 hertz or something, and just keeps going.
So with Phoenix and the camera, like with the perception that I'm doing and we're doing, like, will Nick and the planning team use that perception?
Yes.
How do they use that perception?
So in your case, remember So I guess for everyone else's reference, on Phoenix, what we're doing is we're detecting cones and then planning through the cones. What you're doing, you're detecting the location of those cones. Then downstream in planning, they're taking those cones and finding the midpoint between the right and left. So we plan just straight through them for now. And then our path is the list of those midpoints. That's our path. And then given that path, Nick is doing pure pursuit to have the cart be like, oh, I want to get to the midpoint. What commands do I have to produce in steering to keep the cart in the middle of that path? If, let's say, it slips, it'll give the command to keep it back on track. And then the controls team is taking that set speed and making a controller to actually apply the throttle brake. That's like how it works on Phoenix.
Okay. Cool.
All right. Are any other large questions? Because I think the next is just a cool video, if I remember correctly. Is there more? Is there not?
What do you think about Boolean map for objects, and then you only, where there are objects in your obstacle map, you keep a, what do you call it?
Percentages. Your avoidance map, where you actually keep more than a Boolean value. Because then you would have, I'm just talking about memory optimization, you know.
Maybe. You would have to
Because if
think
there's
about
nothing
it.
in your obstacle map, you don't really care about the percentage of getting through that region.
Well, that percentage is 0.
But it's still stored as a
Yeah, but how would you get that extra storage later?
that's a good question.
You could
You totally
you would have to have an array of what you're talking. If you look up paging and bitmaps. The computer does this to optimize its own memory use. This is how operating systems track used memory. You'll need a second array. You'll need a second bit array that tracks which ones have full percentages or not, and then you'll need a heap, and then you'll need to reallocate your thing on the heap. But you have to have a way to track which ones are floats and which ones aren't, so you can index into that properly. Because some will be parts of bits and some will be floats. So it's gonna be. You could do that, but it would be really annoying
You could also
math.
distort relative map. Be like, it would take up. There's like a balance point. Like if you have your map, which is all Boolean, it's bits, and then where you have obstacles, you store a separate map that stores.
You could have like.
that.
Yeah, you could have like localization is the wrong term there, but you could have a separate cost map.
Localization. I'm not using that definition.
Oh, actually, you could have a cost map on top of your Boolean map to get more data. That's valid. Yeah.
Yeah, and then you store those local maps, right? And that would be inefficient for those regions, but on average would be.
Yeah,
efficient.
that's actually an approach that general approach of like having local maps is actually how a lot of what I've described as a very high level. Like people have done optimizations like yours. You could probably look it up actually. I know Slam, especially vSlam, uses that.
Uses local maps.
Yeah, to only localize within your current region, so you don't just to reduce the complexity, make it faster. But yeah, that is a whole area of
Because I'm trying
research.
to get a balance of optimization and memory optimization.
Yeah.
Because memory is expensive.
Yeah. Honestly, you could just look up research in this area. That's probably going to be the best area. Unfortunately, it's not a huge amount of like textbooks on this, but there's a lot of research into this, from optimization to general representation. Because this is not purely cutting edge. Like this isn't new. This is an old topic from like the 80s, but this
You're just bad at it.
this area of mobile robotics is like just finally getting its strides, in my opinion. Like I went to a factory like an automotive factory back in August, and they just finally deployed autonomous robots that follow like this whole process. And just now, in 2023.
That's funny. I was just
Like, that's crazy.
and they had autonomous robots now.
Yeah, it's like this is still starting. So anyways, long story short, it's still
Well, you-
cutting
you
edge
should
in the grand
figure
scheme
out
of
how
things.
far behind the Army is farther behind than anybody on the planet.
Yeah, in some areas they are, and in some areas they aren't. It's interesting.
Yeah, I mean, yeah, most areas they are. They're pretty terrible at what they do.
All right, I'm showing you the cool video now. I guess. Oh wait, I should skip the intro. This is from Stanford, and they're Stanford, so they're cool. They made an MPC controller, and they were like, I know what we'll do. Well, let's make a DeLorean drift autonomously, and then they made a hype video about it, and it's very funny.
It's really cool.
It's crazy.
They basically detect when they gain or lose traction and adjust their values.
Yeah, statistically, using like using an MPC controller.
That's awesome.
Yeah, it's crazy. Like again, the level of complexity you can get with this is ridiculous. Especially if you start getting like control theory at the tracking level. Like you can control for things like vehicle dynamics. It's just really hard. But yeah,
How long did it take them to do this?
it's part of a research paper.
A month and a half, maybe.
It's part of a lab, so this is like part of the research, and they just deployed it. But yeah, it's Stanford. I have no idea, but they're very smart. I know that much. They also have the budget to do this, which I think is very funny.
Are they running through that computer he's holding?
Yeah. Oh, or he might just be
What if
debugging
that's
it.
feedback?
It's a lab. It's a lab there. So these are like grad students probably. Anyways, I love this video as proof of like, this is hard, but we can do this, so who cares?
Yeah, and Tesla can slam their cars into civilians. Why are they doing
That's because they didn't have Stanford students or something. I don't know.
Is that like Elon Musk touch it?
No, that's just because it's hard in the real world. All this is still an unsolved field, which is why it's fun. Because you can regularly run into issues that people just don't know how to solve yet. It's like your stupid senior design fix could be viable. Like, generally the issues we have are so complicated that like reasonably you have to be pretty good at it to solve it. But still, like there are a lot of areas like, especially in like the perception side of things and SLAM localization, that if you make an incredible like thought of like, oh, like this, obviously we can just use X for Y, like it's still a new field that could actually be viable, and I think that's fun. Probably won't do that in ISC, but in a total career, it's pretty cool. Yeah, that I don't know if I have another slide. I don't think I do. Anyways,
Dang.
that's all. That's my summary in an hour and 20 minutes
What are we doing?
or so. If Tiny Cart doesn't look like this, I am getting very, very sad. But yeah. If you have any questions about this kind of stuff, just ask me. Obviously, this is an absolute info dump. I'm aware of that. But like, if you can understand this, you understand up to like the end of undergraduate mobile robotics, in my opinion. Like, this is about my perception of the whole thing. I think if you can understand this, you'll get a very good grasp of what we're doing, at least in ISC. But even just in industry, like from what I've been told, this is not far off. Like the overall structure is the same. It just gets way more complicated under the hood. But like, if you can understand this high level, this is a very good starting place. And if you can comfortably understand where these things relate, you can start to talk with people in industry and then learn more. And that's where a lot of fun. Where like, you can talk with like Magna or whatever.
GPSs are like 1 meter
Yeah.
precision. That looks like we need like.
Alright, leave a like. No.
I think we need a.
Yeah, like and subscribe for more videos. I would appreciate it. Thank you.